As key exchanges, both the ephemeral Diffie-Hellman key exchange EDH as well as the ephemeral elliptic curve Diffie-Hellman key exchange ECDHE serve the purpose for Alice and Bob to arrive at a shared key that they can use later to symmetrically encrypt data without this shared key ever having to explicitly be exchanged, but both Alice and Bob calculating this shared key by themselves. To achieve this, both Alice and Bob need to send each other half keys, which are simply ingredients into calculating the shared key, but with these half keys revealing nothing about the shared key that they will ultimately arrive at. For the classic Diffie-Hellman key exchange, both Alice and Bob make use of a publicly defined pair of numbers G and P, where at least P is a large prime number and G is often set to just a value 2. Then both Alice and Bob each create a secret, X for Alice and Y for Bob. Then the half keys are calculated as indicated here on the slides and exchanged. Having exchanged these half keys, both Alice and Bob can then calculate the shared key, which they can later use for the symmetric encryption of data. This principle of exchanging only half keys, but not the full key, has also been transferred into the setting with elliptic curves, which on a conceptual level works exactly the same, but makes use of elliptic curves as the underlying mathematical entities. The two primary elliptic curve-based exchanges are X255-19 and X448, both working exactly like shown on this slide to exchange half keys, but making use of different underlying elliptic curves. How both a classic ephemeral Diffie-Hellman as well as an elliptic curve-based Diffie-Hellman key exchange can be used in Python, I will now demonstrate. In a first part, I demonstrated how to use the classic ephemeral Diffie-Hellman key exchange. The first step is to generate public Diffie-Hellman parameters, where I, for demo purposes, opted for a prime number P only of size 512 bits, whereas in production, the prime number should at least be of size 2048 bits. From these public Diffie-Hellman parameters, a public-private key pair of both Alice and Bob could be generated. In order to demonstrate that the half key of Alice really satisfies the definition given on the slides, I asserted that the half key of Alice is the generator G to the power of Alice's secret X in the field given by prime P. Along the same lines, I could generate the public-private key pair also for Bob. Having the public-private key pairs and the half keys ready, I could then have the exchange take place and have Alice create the final shared key by taking in the half key of Bob, and for Bob to create the final shared key by taking in the half key of Alice. Again, I thought it interesting to see that the shared key of Alice really is just b to the power of x, and that the shared key of Bob really is just a to the power of y. Ultimately, I asserted that the shared key of Alice is the same as the shared key of Bob, which once the program ran, proved to be true. Going into demonstrating the elliptic curve-based Diffie-Hellman key exchange, I had to decide on the actual exchange and opted for X255-19, which is the exchange working against the underlying elliptic curve called curve 255-19. Demonstrating the use of this elliptic curve key exchange was then quite a short thing to do. The public-private keys of Alice and Bob are easy to create with the cryptography library. And once the half keys were exchanged, also this key exchange proved that the shared key calculated by Alice and the shared key calculated by Bob were the same.